All right, so what I want to do in this video is I'm going to give you a little bit of the background that I was going to give you in class today. Obviously, we don't have class today because of a water main break, but I wanted to give you a little bit of background, and then I'm going to send you a worksheet for you to do a few practice problems. And then my plan is to lecture like usual on Wednesday and Thursday. So we won't do a worksheet tomorrow. We'll lecture and then do our usual lecture on Thursday. So what we were going to do today in section 15.1 in class was we were going to start talking about double integrals. And double integrals are going to be basically the analog of, in Calc 1 and Calc 2, we talk about single integrals, and we use those to evaluate area underneath the curve. And so if I have a function that's positive, say from A to B, we know how to set that up. We've seen this story before. So what we can do is we can split up our region into lots of little thin rectangles. And then we know that as we take more and more rectangles, as we take a limit, the sum of those rectangles, so if let's say each of these rectangles has width delta x, and then the height is going to be f of xi, where I is some sample point here. Xi is some sample point in the interval. So this is usually x0, x1, x2, all the way up to xn. If we take the limit of that quantity, so here we're taking the area of the rectangles, where the height of the rectangle is determined by the value of the function. And if we take the limit, then what we get is the exact area, which is the integral. And we know by the fundamental theorem of calculus that that has to do with the antiderivative. And we know how to evaluate those. So that's what we're going to do. But instead of thinking about functions of one variable like we did here, so we have y equals f of x, what we're going to do is we're going to think about the scenario in 3D. So when we have multivariable functions. And so here's the picture setup. Here's what I want you to think about or look at. So let's say that I have a function here. So this is now the Calc 3 version. So this is a function z is f of xy. And what we're going to do is we're going to start by integrating over these rectangular regions R. So R is going to be the set of all the values. It's the set of pairs x and y, where x is between a and b, and y is between c and d. Sometimes I like to write this as the interval from AB cross CD. So this is, that cross there is called a Cartesian product. You can look that up if you want to know any more about it. But that is the notation that we'll use for the most part, is that AB cross CD when we're talking about rectangles. And so we're going to do basically the same idea of what we did in Calc 1, just we'll do the analog of it in higher dimensions. So what we're going to do is we're going to take our region, we're going to split it up into pieces. So we're going to take our rectangle and split that up. We're going to make a little grid. And then we'll do the same in the y direction. We don't need to have the same number of lines in the x and the y direction. I don't care if our rectangle is really a square. I don't care if the little pieces that we split it into are squares or rectangles. We'll just assume in general that they're rectangles. Let's assume that one of the areas of this rectangle, so let's assume that one of those areas is dA. So the way that this will work is we're going to take our function and we're going to say that the height of the rectangle is going to be determined by the value at that point. So just pick one of the points in the rectangle, and then whatever that point is, maybe it's the point closest to the origin, maybe it's whatever. Just pick any point in that little rectangle, the sample region, and then that point will give us the height of our box. It's not a rectangle anymore. I guess it's a box. And so we're going to do this for all of the different regions. And then when we add them up, what's going to happen is we'll get an approximation of the volume that we're looking for. So when we do this for all the different rectangles, we get not quite the volume that we're looking for, but it's a good approximation. And of course, to get the exact answer, what'll happen is we'll take a limit. And so when we take a limit, we get a double integral. And so this is the way that we'll write the double integral. It'll be the double integral of f of x dy, f of xy, I'm sorry, dA. The dA tells us that we're integrating, it's a double integral. We're integrating over some area in the xy plane. In this case, it's a rectangle. So I'm going to integrate over that rectangle R. And this is going to be the limit. We'll talk about what goes to infinity in a second, but this is going to be the limit as I goes from 1 to n. So let's say that we split up our interval from A to B into different pieces. So say x0, x1, x all the way up to xn. And then for the y's, we do the same thing. Maybe we'll call it y0, y1, up to yn. And so when we put everything together, we're going to have the sum in the i's. We're going to have the sum in the j's. And maybe I should call this ym. So otherwise, I'm assuming I have the same number of partitions in the x direction as the y direction. And then we'll have f of xi, yj times the area of one of those little subregions, which I'm calling delta A. And so what we'll do is we'll take the limit as n goes to infinity and as m goes to infinity. That was a terrible m. But that's the idea. So we're going to take that limit, that limit of a Riemann sum will turn out to be an integral. And then let's actually go through and let's actually compute one or two examples here. So let's say I want to compute the double integral. So say from 0 to 1 and from 0 to 2 of 2x plus 6xy plus y squared dx dy. Now, in this case, when we integrate over rectangles, it turns out not to matter. The order, whether we do x first or y first, doesn't matter. What does matter is we're going to work from inside out. And so the inside differential, dx, will correspond to the inside integral sign. And likewise, the outside differential dy will correspond to the outside integral sign. And so we have to be consistent there. But other than that, what we'll do is we'll treat this as what's called an iterated integral. And so the idea with that is that we're just going to basically put some brackets around the inside integral. So everything will stay the same. So this is 2x plus 6xy plus y squared dx, put some brackets, dy. And then we're going to evaluate the inner integral with respect to x, treating y as a constant. Okay, so we're back to the partial differentiation thing of treating y as a constant. And so this is going to be, let's see, if we integrate the inside here with respect to x, this will end up being x squared plus 3x squared y plus y squared. And x is going to go from 0 to 1. Now, when we plug in our values for x equals 0 and 1, we'll get a function of y. And we'll see what happens there in a second. This will be the integral from 0 to 2. Let's see, when we plug in x equals 1, we're going to end up with 1 plus 3x squared y. Oops, I'm sorry, x is 1. So 1 plus 3y plus y squared. And when we plug in x equals 0, we get 0, because this is a polynomial in x. I'm missing an x there. And so let me do that. Let me just take that back one step here. When we plug in x equals 1, we get 1 plus 3y plus y squared. When we plug in x equals 0, we get 0, because this is a polynomial in x. And so now we've reduced this to just a single integral. This is basically just a Calc 1 integral. We have 1 plus 3y. I don't even actually need to rewrite that. We can just evaluate that directly. So this will be 1 plus, so if we integrate 1, sorry, we'll get y. Integrate 3y, we'll get 3 halves y squared. Integrate y squared, we'll get 1/3 y cubed. And then we'll plug in y equals 0 and y equals 2. And again, when we plug in 0, we get 0. That's fine. When we plug in y equals 2, it turns out that we'll get 32 thirds. Okay, so we'll get, let's say 2 plus 6 plus 8 thirds. So 8 plus 8 thirds, 24 thirds plus 8 thirds, or 32 thirds. Okay, and that's it. Now, it turns out that there's a theorem here of, it's called Fubini's theorem. And Fubini's theorem basically says that if you're integrating over a rectangle, so if you're integrating over a rectangle, if you have this integral f of xy, there's a few versions of Fubini's theorem, but you have f of xy, and you integrate over this rectangular region, then this is going to be, you can switch the order of the integrals. I'm writing this terribly. So if we have dx, dy, so if x goes from A to B, y goes from C to D, we could just rearrange, and this will be dy dx, where y goes from C to D, and x goes from A to B. So we're really just rewriting that. We also have one other aspect that's sometimes called Fubini's theorem. And that is that if we have an integral, like if we have like x squared times sine of y, something like that, and we're going to integrate, say, dy from 0 to pi, or dx from 1 to 3, something like that. It turns out if we go through this process, that's going to be the same as if we actually just separate our integrals. So if we integrate, let's just think about this kind of intuitively here. If I were to think about this as an iterative integral, meaning that we just do one step at a time, and if I were to put brackets here, when we integrate with respect to y, our x squared is a constant with respect to y, and we could bring that out. So this will be 1/3 x squared, and then we'll have our integral from 0 to pi of sine of y dy, dx. And then notice that actually this is just going to be some number. This is just going to be some constant. And so we can bring that out of the integral because that's also a constant. And so this will turn out to be the integral from 0 to pi of sine of y dy times the integral of x squared from 1 to 3. And so we can separate our integral like that. And so that is another useful facet of this. When we have an integrand that's one function of x times another function of y, we can separate our integrals when we have a rectangle as our region that we're integrating over. And so it turns out that rather than go through all of this together, we could just evaluate these separately. And it turns out that the integral of sine from 0 to pi will be 2. The integral of x squared from 1 to 3 will be 1/3 x cubed. So that'll be 1/3 of, let's see, x cubed. So 3 cubed minus 1 cubed. So that's going to be, let's see, what is that? It's going to be 2/3 times 26. So 52 thirds. Okay, so that's what that integral would turn out to be. Again, using this second one's not always called Fubini's theorem, but this is really just a property of iterated integrals. Fubini's theorem really tells you that if you have a function and you integrate with respect to x or y, you can switch the order when you're integrating over a rectangle. Okay, so that's the first part of what I wanted to share. The second part, and really what we're going to get into in 15.2, and so I will spend some more time with this on Wednesday, but we're going to integrate over more general regions. So let's say I wanted to integrate over a rectangle. So I'm not going to draw the 3D picture anymore. I'm just going to draw, instead of a rectangle, let's say I want to integrate over a triangle. So let's integrate over, this is the line y equals 4 minus x. So this is the 0.40, this is the 0.04. And then we're going to integrate some function over that triangular region instead of integrating over a rectangle. So 15.2 is all about integrating over just general regions. Okay, so we'll get into some details here. I just want to do one example. But what we're going to do is, let's say I want to evaluate the integral of 4x plus 3y plus 2 over this region. Let's call this region D. Okay, so we're going to integrate over this region D. What we need to do is we need to think about how can we split up our region to describe what's happening. And so the way that I would like to do this is I'm going to first figure out where does y go to and from. And so it looks like if y goes to and from the bottom line of the triangle to this side or top line, then I guess it's the hypotenuse because it's a right triangle, but it's just that longer line of the triangle. Y is going to go from 0. So this is y equals 0. And then our y values will go up to 4 minus x. And we're going to have 4x plus 3y plus 2. Okay, so that's where, and actually instead of dA, let me write dy dx. And then our x is going to go from 0 to 4. So generally, this is how these will work in 15.2 is that the inner integral, it will depend on some variable, and the outer integral will have constants because we want a number. And so now what we're going to do is just go ahead and treat this as an iterated integral like we did in the previous section. And so this is going to end up being, let's see, if we integrate with respect to y, we're going to end up with, so we'll have 4xy plus 3 halves y squared plus 2y. And y is going to go from 0 to 4 minus x. Okay, so we'll figure out what that is. And so here we have a little bit of algebra to do, but not too bad. We're going to have, let's see, y is going to be, I like to write y equals, just so that it's clear what we're subbing in, what we're plugging in. And so when y is equal to 4 minus x, we're going to end up with 4x times 4 minus x plus 3 halves times 4 minus x quantity squared plus 2 times 4 minus x. And then when y is 0, we get 0. So that'll be dx. And so now what we'll do is we'll just treat this like a normal Calc 1 integral. And let's go ahead and let's actually evaluate this. This will be, let's see, 16x minus 4x squared plus 3 halves times 16 minus 8x plus x squared plus 8 minus 2x. And so let's see what we can simplify, if anything. This will be, let's see, so we'll have 16x minus 4x squared plus 3 halves of 16 is 24 minus 12x plus 3 halves x squared plus 8 minus 2x. And then let's simplify one more time. These are zeros. So it goes from 0 to 4. We're going to have, let's see, our constant term will be 24 plus 8. So that's 32. And then let's get rid of that. And our x terms, we're going to have 16 minus 12 minus 2. So that should be plus 2x. And then we'll get rid of those. And then we're left with -4 plus 3 halves. That should be -5 halves x squared. Okay, and that should handle the last bits, and it looks like that's everything. So now we just need to integrate. This is going to end up being 32x plus x squared minus 5 over 6x cubed. And we're going to plug in x from 0 to 4. So this will end up being, let's see, 32 times 4 is 128, plus 4 squared is 16, minus 5/6 of 64. So that is, I don't know, whatever it is. This is going to be, let's see, 128 plus 16. This is where I need you, my students, to help me do the algebra. Um, so, uh, yeah, let's just type in. I'm going to cheat. Don't tell anybody. I'm going to cheat and use a calculator. But let's just type in what this is going to turn out to be. So this was 128 plus 16 minus 5/3 of 32, 5/6 of 64. And so that'll end up being 272 over 3. Okay, and so that turns out to be the volume of this function over that triangular region. Okay, so I'm going to leave that to you. I'm going to give you a few problems for you to work on yourself on the worksheet, and then we can pick up from there on Wednesday. All right, have a good day. See you Wednesday.